everybody. Right, this is our next to last class, which always makes me a little bit sad, but I'm also excited to be almost done. So just a few announcements before we start. The TAs kindly prepared a video with the answers to homework number 8. This is because you didn't have a chance to have your discussion section as usual last week. So instead, they prepared a video, and if you go to iLearn and go to the tab where you usually get your homework, you can get a link to a video to the answers to homework 8. And again, a reminder that you do have a quiz based on homework number 9 this week. And also there will be a homework number 10 that I will be posting on Friday. This will not have a quiz. You don't have discussion sections next week, but I'm just posting it there. My computer's telling me that my internet is unstable, so hopefully you can still hear me. Right, so on Friday, I do have a lecture. We do have it as our final lecture. We'll talk about the Big Bang on Friday, but I will also be posting a homework like I always do on Fridays. And there will not be a quiz. On Sunday at 5 p.m., I will be giving a review for the final. So during that final, I will go over the questions on homework 10 so that it'll be like a mini discussion section where I will go over all of them, and then bring your questions and I will be answering questions. I'll just tell you in very rough terms, these are topics that are very important, especially for the first part of the class. For midterms 1 and midterms 2, what are like the big concepts that I really want you to remember and to study? And then after that, your homework is your best friend when it comes to studying for the final. So you should bring any questions that you have from that. And I'll try to make it as interactive as possible, even though it'll be online. So it'll be the same link as the lecture. And so I will be seeing you there. I will record it and I will post it. But of course, I will only answer your questions if you show up. So good, thank you for letting me know that you can still hear me. Yes, I will help you with homework 10. Right, so there's a question about what happens if you got 100% in every single quiz. Will you get extra credit for that? And the answer is unfortunately not. If you got 100% in everything, you'll just get 100%. But that means you're super well prepared and you'll probably do very well in your final. So yes, lecture on Friday. All right. So anyway, so that's, and again, a reminder that there is a final exam in person Wednesday, December 8th from 3 to 6 at the University Lecture Hall. You need to bring a Scantron with you. And you need to fill in your student ID because sometimes people don't know it, and students don't forget their student ID, and it's not in your ID. I understand. So make sure you look it up and you fill it in and you come in to the exam with that ready. If you usually get accommodations for your exam, make sure that you contact our Ability, the student, I forget what the official name is, but make sure you contact them so that you can arrange alternative location arrangements, whatever else you need. Because so far I've only gotten one request, and I know that there's a lot more of you who will need some accommodations. So make sure you do that. Make sure you don't miss your deadlines. Very good. All right, so I think that's all for announcements, and we can move on to the lecture. So like I told you before, we talked a lot about the nearby universe, right? The galaxies that are near the Milky Way and smaller scales than that, galaxies and stars in our galaxy and solar system and other planetary systems. That's what we focus for the most part in this class. This last week, we talk about the very big, the entire universe. Other classes that deal with this are physics 5, the history of the universe, physics 37, origins, physics 166, if you're either an engineering or a physics major or a math major, you can take that. That's an upper division cosmology class, right? So those classes deal with this. But in this class, I just want to give you a little taste of what cosmology and the study of the entire universe is like. Last time, we talked about the fact that the universe is expanding, and that implies that at some point everything was in the same place at the same time. And so that means that the universe had a beginning. And when we measure the expansion rate of the universe, we think that beginning was about 13.7 billion years ago. And so I ended the class by saying, I think this is profound. I mean, to me, at least, it seems kind of amazing to think that time had a beginning. It hasn't always been there, right? Time there, and like I said last time, there was a time when there was no time. So today we are going to see how the fact that the universe has only been around for so long, for 13.7 billion years, also means that we can only see so far, right? Like we can't see to an infinite distance. How far we can see in the universe is limited by the fact that the universe has an age. We'll talk about that for the next few slides. And then we're also going to talk about what happens in the future. So does the universe continue to expand forever, or does it reverse, or what happens? That's what we will spend the rest of the class talking about. Oh, there's a quick question about the test. Can you use mechanical pencils, or do you have to use number 2? Number 2 pencils work the best, so I recommend that, but mechanical pencils do work too. So yeah. All right, so is there a limit to how far you can see in the universe? For example, this guy is standing on a mountain and looking at the horizon, right? The horizon, what is the horizon? It's just how far you can see on Earth, right? And the fact he can't see to infinity on Earth. There is a point where he gets to, the circumference of the Earth, and then he was not going to be able to see beyond that. Then we call that the horizon. The same thing is true in the universe. We cannot see out to infinity. And the horizon to which we can see is given by the age of the universe. So why is that? Well, we've been talking a lot in this class about how light takes time to travel. And it takes 8 minutes for an image of the sun to get from the sun all the way to Earth. So we see it as it was 8 minutes ago. And we talked about, the other side of our galaxy, 50,000 light years, or the center of the galaxy, 28,000 light years from us. So we see it takes 28,000 years for an image of the center of our galaxy to get to us. So same thing with galaxies, right? Like you can see a galaxy that is 5 million light years away. It takes 5 million 5 million years to get here. Well, at some point, you're going to be looking at galaxies that are billions of light years away. And you can only see things things that have had enough time for its light to get to us, right? So we can only see objects whose light takes about 13.7 billion years or less to get to Earth. Because if they're farther away than that, if it takes longer for light to get to us, then we still haven't had a chance to see them. And so this is what marks what we call a cosmological horizon. This is how far we can see. It's the radius of the observable universe. If we're here in this galaxy at the center of this picture, then we're only going to be able to see objects inside this cosmological horizon. Objects that are further away, let's say there's a galaxy out here. Well, its light starts traveling. It travels for 13.7 billion years, which is, how long the universe has been around. And it just hasn't had enough time for the light, for the image of that galaxy to get to us. So we cannot see objects that are beyond the cosmological horizon because their light has not had enough time to reach us, right? So basically what this means is it doesn't matter how big the universe is, we can only see out to a certain distance. And we cannot know what's beyond that. We assume that beyond that, the universe keeps going and that it looks pretty much the same as what it looks like from here because of the cosmological principle, right? The universe looks about the same regardless of where you are within it. But we cannot see. So it's not a matter of technology. We could build the biggest telescope in the world, the biggest telescope in our solar system, and we still wouldn't be able to see beyond this cosmological horizon. So the observable, what we call the observable universe, the universe that we can see, extends to what we call a look back time, right? That's the time that it takes for light to come, of about 13.7 billion years in every direction from your point of view, from Earth. Yeah, so why 13.7 billion years? Because that's how long the universe has been around. And things beyond that distance, the light just hasn't had enough time to get here. As the universe ages, as time goes on, you will be able to see out more and more. But at the same time, the universe is expanding. So in fact, you end up being able to see less and less as time goes on. So imagine that you have aliens who live on a planet around a very distant star, right? So we're here on Earth, and so you have aliens, around the star A or aliens around star B. And what they will see, the cosmic light horizon or the cosmological horizon, is going to be different from what we see here, right? Everyone will have a radius of look back time of 13.7 billion years around them. So they'll be able to see different things regardless of, depending on where in the universe you are. So all of that is to say, there is a limit to how far you can see, simply because the universe has only been around for so long, for 13.7 billion years. All right, so what we're gonna do for the rest of the class is to talk about the fate of the universe. What will happen to the universe? And then it's a little bit backwards because today we are gonna talk about the end, and then next class, our very last class, we will talk about the very beginning of the universe, what we know about the first few seconds, the first few minutes of the universe. So the question we're gonna answer today: will the universe continue expanding forever? All right, so let me show you a video just to introduce what we're gonna do for the rest of the class.
A battle is taking place in the farthest reaches of space. No one can see it, but scientists are certain that it's happening and that the outcome is grim. The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball, as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
I have a question for you guys. Is the sound okay? Because I actually can't hear anything. So can you hear the sound of the videos? Yes, you can. Okay, great.
Yes.
I think thank you. I appreciate it. Oh, it is low. Okay. Yeah, I don't know why it was fine when I was preparing the class, but right now the sound went way down. Yeah, very quiet. I don't know how to make it better. Okay, well, hopefully you can hear the next one better. I put on my earbuds to see if I can hear better. I hope it's okay. Let me try the next one because I have a video coming up. Let me just say, so we're going to talk about the possibilities, and the possibilities depend on whether the universe continues to expand or if it, let me actually on. Okay, so I hope you can hear me. So
Yes,
whether it continues to expand or if it reverses. You will see in your textbook that there is a plot that looks kind of like this. You have time going from the Big Bang, from the beginning when the universe started expanding to, the future. And then on the other axis, you have how much the universe expands. And it's some sort of a length, right? Like how far apart are things from each other, like galaxies from each other in the universe. So this plot, if you have a universe that expands and then it contracts again, you will have something that goes up, up, up in expansion, and then it turns around, and then it goes back to zero expansion, right? To zero length. Or if you have something that continues to expand, then it won't come back down. So you'll see that plot, and I'll come back to this in a little bit. So basically, the question that we're trying to answer is, does the universe have enough kinetic energy from the expansion, right? Kinetic energy just means the energy from motion. So does the universe have enough kinetic energy to escape its own gravitational pull? We talked about before about how gravity, like as an analogy, gravity here on Earth pulls things down, and I can throw, I have my mouse, which you probably can't see. So if there's my mouse, I can throw my mouse up, and it'll go up for a little while, and then it'll come back down. If I throw it a lot harder, it'll go a lot higher up, but then it'll come back down. But if I throw it really, really high, really, really fast, with a lot of kinetic energy, so that I reach the escape velocity, then my mouse will just continue to go and it will leave Earth. So the analogy here is the entire universe has mass, and it's that mass of the universe is pulling the universe onto itself. So does the expansion have enough kinetic energy, right? Like the push that I would have to give the mouse. Is it strong enough that the universe will reach its own escape velocity so that it'll continue to expand to escape forever, right? And so I found this video on YouTube that sort of explains the different possibilities, and it gives a different analogy from what I gave before. Like last class, I kind of got excited about the sea otters that hold hands in the water to avoid being spread by the current, by the water current. So this one gives a different analogy, like rubber bands, but let me play that and hopefully you can hear it. So I'll play.
Rated rate. But what about the future? Do we know how our universe is going to end? Cosmologists have 3 possible answers for this question, called the Big Freeze, the Big Rip, and the Big Crunch. To understand these 3 scenarios, imagine 2 objects representing galaxies. A short, tight rubber band is holding them together. That's the attractive force of gravity. Meanwhile, 2 hooks are pulling them apart. That's the repulsive force expanding the universe. Copy the system over and over again, and you have something approximating the real universe. The outcome of the battle between these 2 opposing forces determines how the end of the universe will play out. The Big Freeze scenario is what happens if the force pulling the objects apart is just strong enough to stretch the rubber band until it...
Okay, let me pause there. We'll come back to the Big Freeze and all those. But let's just keep this analogy in mind. So galaxies are held together by this invisible rubber bands, which is just gravity. So there is the expansion that is trying to pull them apart. And so which one wins, right? As other things that we mentioned in this class, there's oftentimes 2 main competitors. Like in the sun, you have gravity pushing in versus gas pressure pushing out. When you have stars, and in the case of the sun, they balance each other out perfectly. So the sun doesn't collapse, it doesn't explode. In the case of star formation, again, you have gas pressure versus gravity. And in the case of star formation, so that things collapse. In the case of black holes, gravity wins, so things collapse into a black hole, and so on. So in this case, the things that are competing are kinetic energy from expansion and gravity that comes from the average density of the universe, which is usually denoted with the Greek letter rho, but I think this is the only time that I write it like this here. But you'll see it in textbooks. So the density of the universe, meaning the mass in a given volume in the universe, gives you gravity. So you have this competition, expansion versus self-gravity. So going back to the question, does the universe have enough kinetic energy to escape its own gravitational pull? So, well, the first thing you have to ask is, well, how big is the gravitational pull, right? What are we competing against? The gravitational pull of the universe will depend on how much matter there is in the universe, right? As I've been saying again and again and again, everything that has mass has gravity. So if you have more mass, you have more gravity. So how much mass do you have in the universe? So whether or not the universe continues expanding forever depends on how dense the universe is. Now, I cannot tell you how much mass there is in the universe, because I just told you that we can't see the entire universe. We can only see out to a certain part of the universe, out to, a look back time of 13.7 billion years all around Earth. So we can only see the observable universe. We can't see the entire universe. So we can't talk about total mass. Instead, we have to talk about density, because density is just mass divided by volume. So what we do is we count all the mass, all the matter that we see around us in the observable universe, and then we divide it by that volume. So that mass divided by volume gives you density, right? So if you have a lot of mass in a given volume, you call that high density. If you have a little bit of mass in a given volume, you call that low density. So high density in our universe will give us a lot of gravity. Low density in the universe will give us low gravity, right? All right, so basically, given that, there are three possible fates for the universe, depending on the density of the universe. So the three possibilities are that, one, if it's too dense, if it has way too much matter in a given volume, and in that case, gravity ends up winning. Second possibility is that it's just right. They call this the flat universe, or the zero universe, but that's in terms of zero curvature. But anyways, so this is just right. This is when gravity balances expansion perfectly, right? Just like in the sun, gravity and gas pressure balance each other out perfectly. And then the third possibility is that it is not dense enough. So this is where gravity would be pretty weak and the expansion of the universe wins. So let me tell you a little bit more about each of these, and they each correspond to a way in which the universe would end. So we'll start with the first one, which is kind of, for some reason, it tends to be the favorite one for students. So, and for your textbook, this is what the plot looks like. Too dense, number one, that would be what they call a closed universe, where it expands for a while, then it turns around, and then it collapses again. Then there's what they call the flat universe, which is the just right. The universe expands, but the expansion slows down until at infinity, it would balance each other out perfectly. And third one, not dense enough, that's what it's called, an open universe. And that's when the universe continues to expand and it never slows down. So again, all right. So number one, when density is so high that eventually gravity wins. So this is what sometimes is called the big crunch, because at some point, the universe is expanding and it reaches a certain extension and then it reverses. So this is like my mouse when I throw it up, right? It goes up for a while, then the motion reverses, and then it comes back down. And so that's like the big crunch. The universe went off in the Big Bang, it started expanding, it gets to a certain point, and then it crunches, right? It comes back down. So the fate of the universe is to collapse in the end. So let me show you a video of this, and I'll read your questions in the meantime.
What about the third scenario, where the rubber band wins out? That corresponds to a possible future in which the force of gravity brings the universe's expansion to a halt and then reverses it. Galaxies would start rushing towards each other, and as they clumped together, their gravitational pull would get even stronger. Stars too would hurtle together and collide. Temperatures would rise as space would get tighter and tighter. The size of the universe would plummet until everything compressed into such a small space that even atoms and subatomic particles would have to crunch together. The result would be an incredibly dense, hot, compact universe, a lot like the state that preceded the Big Bang. This is the Big Crunch. Could this tiny point of matter explode in another Big Bang? Could the universe expand and contract over and over again, repeating its entire history? The theory describing such a universe is known.
Sorry, it cut early. Let me see if I can go back.
What about the third? Collide. Temperatures would rise as space. Atomic particles would have to crunch together. The result would be an incredibly dense, hot, compact universe, a lot like the state that preceded the Big Bang. This is the Big Crunch. Could this tiny point of matter explode in another Big Bang? Could the universe expand and contract over and over again, repeating its entire history? The theory describing such a universe is known as the Big Bounce. In fact, there's no way to tell how many bounces could have already happened, or how many might happen in the future. Each bounce would wipe away any record of the universe's previous history. Which one of these scenarios will be the real one?
All right, so this is what, like I said, this is what is called the Big Crunch. And then there's this idea, well, if it all goes back to a singularity again, that sounds a lot like the Big Bang. So is it possible that it just Big Bangs again, and then it goes all over again, and then it Big Crunches again, and then Big Bangs again? But like the video said, all the information would be lost, right? So you would not be able to know whether, I mean, you have no idea if this is just a cycle that goes on, or if not, right? But there's no way to know, there's no way to test it. So for some reason, like I said, you know, in the past, I've taken polls, like which universe do you like the best? And a lot of people like this one. And I don't know if it is because the idea that, I don't know, cycles are kind of appealing. And also there's some cool things that we don't really have time to get into. But in this type of universe where there's a lot of matter, the universe is also curved because, you know, gravity causes a lot of curvature. And there are some really cool things about this type of universe. For example, if you were traveling in a straight line for a very long time, eventually you would come back to the place where you started because the universe is so curved. So this is the type of universe that doesn't have edges, it doesn't have a center, but it's not infinite, because at some point you actually would travel the entire universe if you travel for a very long time. So I think those are the reasons why this is an appealing universe for a lot of people. But the bottom line, I mean, the part that I want you to remember about this is the universe where there is a lot of matter, there is a lot of mass. Therefore, there is a lot of gravity, and that gravity wins over the expansion of the universe. And so in the end, it stops expanding, it reverses, and it actually collapses. Yeah, so does time in such a circumstance even make sense is one of the questions. Yeah, it doesn't really, I mean, it makes sense within a given Big Bang, right? But there's no, it's a completely different set of time, you know, for the other Big Bangs. Okay. All right. So the next possibility is gravity balances out expansion. And this, in, you know, very simplified terms, this is what what, as I said, it was either the flat universe, some textbooks calls it the critical universe. This is when density is not high enough for gravity to win, but they, after an infinite amount of time, they actually balance each other perfect. So this universe would stop expanding at infinity, right? And after an infinite amount of time. But in the meantime, it just kind of slows down. It keeps expanding, but the expansion slows down. And so this is sort of the really well balanced universe. And then the third one, well, let me answer the third one. Sorry, so let me answer let me answer a question that was asked before. So, sorry, I'm getting very distracted. Okay, let me get my attention back. So somebody's asking, what would it feel like on Earth if the universe collapsed? Well, I mean, you would get crushed at some point because everything, all the matter will be gotten put together. So all the planets would merge and with the stars, and I mean, you would die pretty quickly. When the contraction starts accelerating and everything starts merging, I don't know if we would first die burned. Probably. I think we would probably die burned because we would be pulled into the sun, right? Or maybe we would crash against another asteroid or planet. I don't know. But I can tell you that if the big crunch ever happens, it will be at a time when the sun is not around anymore. This is a long, long time ago from now, and the sun will be dead by then, and humans will probably not be around anymore. And if we are, we'll be in a different galaxy probably. All right, sorry. So let me go back to the third possibility. The third possibility is that the universe is not dense enough, that the density of the universe is very small. So, and expansion wins. So gravity is not strong enough to stop the expansion of the universe. The fate of this universe is to keep expanding and to never slow down. So this is what, sometimes this theory or this model is called the big freeze. So one of the questions that I had from before is does this mean that one of the possibilities is that the universe doesn't end? Well, it kind of ends anyways because of this. So I actually have a video, I believe. So the problem is that things fly away from each other over time. So eventually all the stars will die. And the problem is you need high densities for stars to form. So if everything sort of moves away from everything else, you know, the density of the universe continues to be lower and lower and lower. And at some point, it'll be so low that you can't form new stars. So unfortunately, even though this is not violent, even though this is very little by little, things eventually get pretty cold. And that's what is called the big freeze. So let me go back to the video that I was showing before to show the big freeze from them.
Will play out. The big freeze scenario is what happens if the force pulling the objects apart is just strong enough to stretch the rubber band until it loses its elasticity. The expansion wouldn't be able to accelerate anymore, but the universe would keep getting bigger. Clusters of galaxies would separate. The objects within the galaxies, suns, planets, and solar systems, would move away from each other until galaxies dissolved into lonely objects floating separately in the vast space. The light they emit would be redshifted to long wavelengths with very low, faint energies, and the gas emanating from them would be too thin to create new stars. The universe would become darker and colder. approaching a frozen state also known as the Big Chill or the heat death of the universe. But what if the repulsive force is
Earth's perspective, the first thing.
All right, so of course, the question that I need to answer is, which one is it? Do we have a lot of density or not enough density or just right? Well, astronomers have been measuring this for a very long time now, for decades, to figure out which one is the right one. And, you know, when I was a kid, this is what all astronomers were trying to do. They're trying to figure out how much mass is there in the universe. And what they figured out, or what we have figured out over decades, is that all of the matter, if you account for all of the matter, all of the normal matter that makes up gas and dust and stars, and also the matter that we cannot see, such as dark matter, if you put all of that together, it amounts only to about 27% of the density that is needed to actually halt expansion, to stop this expansion. So since we didn't find enough matter, then we determined that this implies that the universe will have a fate that to expand forever at a constant rate. This rate is not going to change, right? It'll always be going. It's not going to slow down. It's not going to reverse. You know, it's what they call the coasting universe. But is it true? Is the universe really expanding at a constant rate? And this is something that was, that people, I mean, lots and lots of groups of astronomers were working on experiments that were testing whether the universe was expanding truly at a constant rate. And really what astronomers were trying to figure out was whether it was at a constant rate or if it was slowing down. How do they do this? What you do is basically you measure the Hubble law that we talked about last time. You try to measure it today, and then you try to measure it, you know, 1 billion years ago and 2 billion years ago. Wow, how do you do that? Well, in astronomy, you can see into the past. You can see how the universe was a while ago, right? Because if you look at very distant objects, you're seeing the past. So what astronomers do is they observe galaxies that are very, very distant, right? Oh, I'm skipping ahead. You look at galaxies that are very distant so that you're looking far in the past. And then you measure the Hubble law. What's the Hubble law? Well, the redshift versus the distance to the galaxy. And like I said, about 20 years ago, there were all these groups that were trying really, really hard to figure out, has the expansion of the universe always been the same, or is it slowing down? And much to everyone's surprise, what they found was the opposite. The universe, the expansion of the universe is not constant. It is not slowing down. All the opposite, it is speeding up. And this was a huge surprise. And I actually remember the day that the biggest paper that came out with these measurements, because nobody was expecting that, right? Like, it's like, again, if I throw my mouse to the air, you expect it either to slow down or to keep going and escape Earth. But you never, ever, ever expect it to start going slowly and then speed up, right? And then boom, get out of Earth. And that's what we discovered, that the universe was speeding up. And that was just weird. So here it is, how they did it. Well, actually, I'm not going to get into the details of how they did it because we only have 6 minutes left. But distant galaxies, as they measure them, show important deviations from the Hubble law. And what they showed is that in the past, the universe used to expand more slowly. And in recent, not millennia, right? More like millennia, like in recent millions and billions of years, the universe has been speeding up. So why? I mean, at this point, you need to introduce new physics, right? Physics that we don't know, that we don't understand yet. Because, you know, we know gravity, which slows things down. We know like kinetic energy, which can keep things going at the same rate, but we don't know what could just accelerate the universe. And so people call this, you know, astronomers call this dark energy. If you remember when we discovered mass that we didn't know what it was, we called it dark matter. So now we discovered this sort of energy, this thing that is speeding things up, that is making the universe more energetic. And so we give it the name dark energy, but we don't know what it is. It is some mysterious form of energy that provides a pressure that pushes the universe outwards, and it's causing it to accelerate. But we don't know what it is, right? So dark energy, you know, this cartoon, it's made from, we don't know. We have no idea what it is. So it is an unknown form of energy that could be causing the expansion of the universe to accelerate. This, by the way, was also kind of anticipated by Einstein's equations of general relativity. But again, this is not something that he thought of as being a real thing. It just happens that his equations, Einstein's equations, actually account for this dark energy. So when you take that energy that is causing the universe to expand faster, and you sort of get its mass equivalent, right? If you put it in terms of mass, then the composition of the universe as we understand it today is something that you would never guess, right? All of the matter that you see, or ordinary matter, right? Like what my head is made of, and what the earth is made of, and what stars are made of, and all the gas in the universe, all of that accounts for a mere 5% of the universe. Everything that we see, right? Dark matter, that's the one that we know, we understand it pretty well. It's made of, we don't know of what, but we have some pretty good ideas of how it acts. We know that it's mass. We know that it causes light to bend. We know that it causes stars to go faster in the outskirts of galaxies. We know a lot about dark matter, but it's still mysterious because we don't know exactly what it's made of. That is 27% of the universe. And then there is dark energy, which is this thing that we have absolutely no idea what it is. And that is, as far as we know right now, about 68% of the universe. A little bit depressing, right? Like everything, my entire career has been dedicated to about 5% of the universe. A little bit of dark matter, and you know, never mind like someone who does biology. They are basically studying, you know, less than 1% of the universe, and the rest of it is something we don't even know what it is. I do want you to remember not these precise numbers because they will change, I guarantee you, over the course of your life. They, you know, people are constantly measuring these things and they change, but I do want you to remember that dark energy is the vast majority of the universe, probably about 2/3 or so. And then dark matter is another big chunk. And then ordinary matter is just a very, very small, or not very, very, but a small fraction of the universe. So, all right, so the fate of the universe then is to expand forever. The ultimate fate of the universe depends on whether dark energy gains strength over time or not. And we don't know. We don't know if it will gain strength or not. If it does gain strength, then the universe will end with a big rip. A long time from now, not anytime. What is this big rip? Well, things start to get far away from each other, like in the big freeze, but in the end, it'll expand so fast that, you know, everything will rip apart. And I don't have time to show the rest of the video, but you can look it up on your own. And it just shows you how this would happen. But here's the thing. We don't know very much about dark energy yet. There's a large fraction of my department that are trying to figure out what dark energy is. So it is too early to tell. We don't really know if the universe is going to end with this big rip, or if it'll just sort of freeze, or what. It's not very likely that it'll crunch again. That is the least likely of the possibilities. So anyways, I will leave it at that. Let me just leave it with this picture. So the big rip is what might happen, but we don't really know yet. The good news is it's a very long time from now. So on Friday, we will have our last class, and I will be talking about the very beginning of the universe, the Big Bang. And and then on Sunday, I'll see you for the review. And if you have any questions, please stay behind and I will answer them. So let me stop recording and I will see you on Friday.